Let's begin our class. Before John talks, let me just say the music was from the suite of pieces called The Planets, and that happened to be a planet Jupiter, that a man wrote a music, The Jollity of Jupiter. I don't know that Jupiter is particularly jolly, but we'll see why that's appropriate for today's lesson. But John, one of your classmates, has some experience using capacitors in, he'll explain it. Oh, John, here.
No. I'm loud, right?
Speak to the lady.
Okay, so here I just did a little schematic here of a stereo setup. You guys know when you have subwoofers in your car and they draw a lot of power and they make a lot of sound in the back. They're driven off an amplifier, and the amplifier asks for power from your battery. But if the subs draw too much power and you can't supply enough,
This will go on the record.
we can. Oh my goodness.
Feels
We
good,
can. You can put capacitors in between, and the capacitors will store the charge and then provide it to the subwoofer when it draws a lot during heavy bass or something like that. And then you'll notice that if you don't have capacitors and your subs are too big, the lights inside your car can dim a little bit. So that would be coming off of this, and it wouldn't be, it'd be drawing too much. So your interior lights would dim, and with the capacitors, you can avoid that. They'll provide the charge to the subs, and you can keep your lights inside and a good loud stereo. And that's my thing.
Bravo. Okay. Thank you, John. So capacitors are for real. And those of you who have these booming cars know how it's done. But I'm going to talk a little bit more about capacitors and their utility. I started on this last time. I have to go very quickly because you're getting into magnetism, which is a whole different subject, and we have to move along to that. But I wanted to just remind you of a few things about capacitors. Namely, you want to understand the difference between the capacitors as a circuit element and resistors. Now, resistors, you recall, you're doing your homework today, and it involves in your lab, there were two different possibilities that we will deal with. Namely, you could put two resistors in series, R1 and R2, and if they're in series, they're aligned such that the same current flows through both. If you have an EMF, you'll have a current flowing through these two, and this can be made equivalent to a single equivalent resistor. And equivalent means that this one resistor, R equivalent, will have the same current flowing through it, and will have the same voltage drop as across these. That's what we understand by equivalent. And we have a result for that the equivalent in the case of series connection is the sum of these two, which is physically plausible. Namely, you're trying to push current through two obstacles. If you have two in a row that you have to get through, the resistance is greater than any one of them, because the overall resistance, you got to get through one, you got to get through the other. So the overall resistance is the sum of the two resistances in series. Well, we had the funny situation where you could put those resistors in parallel, namely put one here. Now here's the perhaps less intuitive thing. I have one resistor, R1, and current is flowing through it. Now if I put a second resistor in parallel with it, the resistance, you have not only current going, see the voltage is the same across this one. Now if I put a second one in parallel, the voltage is the same across the second one, therefore current will also flow through the second one. And because there is greater current Yeah, and the important is that the resistance is voltage over current in every case. Because I have this current flowing both through 1 and 2, the resistance sees more current. So because this is larger and the voltage is the same, this equivalent resistor is less because there's more current. As far as the battery is concerned, it looks out and says, I have one resistor here, and it's both I1 and I2 are flowing through it, and I have the same voltage. It must have less resistance than either one of these, because either one of these, I1 is equal to R1 over V. No, I1 is V over R1. And I2 is V over R2. So the current flowing through just the equivalent resistor is the sum of the two, and so the equivalent resistor has less resistance because there's an additional path. It's as simple as that. So that's kind of intuitively obvious. What's less obvious is what goes on with a capacitor. A capacitor is given by Q over V, or V is equal to Q over C. And if you have capacitors in series, say, by analogy to here, I put a battery on this one, C1 and C2. Now, you might think, well, I have two in series, I'm going to have more capacity. But the problem is that now if you look at the formulas, you might get suspicious about that conclusion. Because if you look at the capacitor has a Q in the top, and the analogous thing with the resistor is the current, right? Because current is charge per unit time. So, but you see, here it's on the bottom, here it's on the top. And here, the resistance, the voltage is on the top, but here, the voltage is on the bottom. So you might get suspicious that maybe this kind of setup is going to be different from having series resistors. In fact, things may get reversed because, you see, the position of the current and the voltage is kind of reversed here. So that would make us a little suspicious. So in any case, when you actually do it, you will find that the equivalent capacitor in series, if those are going to be equal, it's going to turn out that, in fact, the 1 over C equivalent is going to be 1 over C1 plus 1 over C2. In other words, the equivalent resistance is going to be less when they're in series. C equivalent is less than either C1 or C2. You have less capacity if you put them in series. That's not very intuitive because we don't have a very good intuitive feeling for capacitors, but it works out in the math, and I can give you some analogies which will, if you want a better physical feeling for it. But just intuitively, the fact that these formulas, the definition of the items have that difference, and likewise, the formulas are sort of reciprocals of each other, you might expect that that case is going to be analogous to this one, and this one is going to be analogous to this, namely that if you have two capacitors in parallel, C1 and C2, that here in parallel, the equivalent capacitance, now it's equal to the sum. Now this one I can give you a little bit of a feeling for if I said that the capacitor is like a tank of water, and I have one tank that has a big area, and I have another tank that has a small area. And if I fill them up to a certain voltage, see, because the voltage is the same across these, if I fill them up to the same height, I don't know if I did that accurately. No, I didn't. If I fill them up to the same height, the capacity, if I fill these to the same height, the capacity is the sum of these areas. So here I could say that the capacity, the equivalent area is the sum of the area 1 plus area 2. So I'm using this now, that analogy I mentioned to you, that you could regard the capacitive situation as the area of the can, and this represents the voltage, or the height represents a voltage applied. So if I have the voltage the same, and I have two different areas, A1 plus A2, that the equivalent of that would be one larger can with a bigger area. A total is A1 plus A2. It's a slightly different story here, because here it's a long-winded story to use the same analogy to get that result. But in any case, this is the way things work. Now, so you have to know that, and you can sort of see that the capacitors and resistors have some features in common, but not, they're sort of reciprocal of each other. So now, let me see, moving on to, so I do capacitors in series, capacitors in parallel, and then, oops, you see, just happened, I jumped over this thing. Now, it turns out, I want you to see this, I've been having trouble all semester with this blankety-blank thing. It turns out that trackpads work by capacitors. The point is, what they do is they have a series of lines going this way and lines going that way, and in between is an empty space. And that's a capacitor. So you put charge on this and this. In fact, these are so small that there's actually a little leakage of the electric field, around the edges. So the point is that when you put your finger there, you actually, let me show you the next slide, if I dare. Here I am, bald-headed and everything. See, if I go here, I'm adding a capacitor, I'm kind of a fairly good conductor. And so I'm adding another capacitor in parallel with this. So I'm changing the capacity. If I keep the voltage constant, and I change the capacity, in order for if this is a constant and this is changing, then Q has to change. The charge on the capacitor has to change, which means current has to flow. So when they see current flowing, it means somebody came near that place, near that capacitor. So it's a way of locating where my finger is, because I'm changing the capacity and I'm causing current to flow. So I figured out, finally, that I could defeat this thing by, let's see. See, I can move it with my, see, again you did it. But now I'm going to increase the space between the capacitor and my finger, so I'm going to make it less coupled to the capacitor. Let's see. I did it again. There we go. So where is the arrow? Come on, guys. But now if I put a piece of paper here, oh, it went away. I can't get both at the same time. See, now if I move my finger, the arrow doesn't move. You see that? Oh, it did. But it's much, much less sensitive because I've gotten, these things, they really are very sensitive, but if you get farther away, the field leaking out is much less as you go further away. So by just doing that, I've cut down the sensitivity. But if I really push on it, it works. But I think it doesn't, at least I've got it not jumping. Now, if I take away half the sheet, this is just ordinary tissue. One sheet I thought worked. Yeah, but it's much kinder to me, right? You see that? And it doesn't jump nearly, so I'm going to leave that on. Maybe I'll even glue it onto this thing because it's just an awful nuisance, isn't it? So I learned something, thank God, how to control this monster here. Okay, so no, I'm going to leave it here. This is really good. Okay, now the other thing I wanted to mention to you, I went the wrong way now that I've got it under control. Now, the typical capacitor, they don't put airspace in here. For example, it would be very hard to do, to manufacture wires and keep the space empty, because how do you control it? See, things would float around, push down. So they put some stuff in between. And it turns out that if you put stuff in between, you want to have an insulator because you don't want it to conduct through. So the typical capacitor actually has some material in between. So it really looks like this. And this material they put inside cannot be a conductor because then it would simply be a resistor if the conduction would really come through. So you need an insulator in between, and in fact they call it a dielectric, because they're using the polarization properties of this material. In fact, you see, I don't know if we derive very quickly the capacitance of a parallel plate condenser, and it came out to be A over epsilon naught D. No. It was epsilon naught on the top. Yeah. So it was the area and the spacing. Now, what I just did with this piece of paper is I increased the spacing between my finger and this, because the capacitor leaks a little bit. It has field in here, but the field bulges out at the edges. So when I put my finger here, I was connecting to this thing. I was making a capacitor in parallel with the one that was there. So that's how I manipulate the trackpad. And by putting a piece of paper here, I ensured that I was further away. I was increasing the D and reducing the capacity that I was contributing here. Now, it turns out that when you put a material between here, the capacity actually increases by a certain constant. Now, the reason for that, even if you had the same spacing between the plates, and I just put some stuff in there, although D is the same, what has happened is the capacitance increases by this constant. So it's as though, and it is true, that more charge goes on to the capacitor. I'll tell you very briefly what happens, and that is that suppose I have the plates charged, plus and minus, and I have this stuff in here. What happens, of course, is that we've talked about the material here polarizes, so that negative charges, let's say even if it's one of those materials that has no dipoles in it to start with, it polarizes and you get some dipoles. You stretch the atoms or molecules, something like this, right? We've said that many times. This is your ordinary, simple dielectric. So, the reason that the charge goes up is that, you see, now you put some charge on this plate to produce the polarization here, but now you got some negatives nearby that plate. So more charge can come and join, because it sees nice negatives over there. So the Q actually increases, depending on how many minus charges are appearing near that surface. So actually, this constant here is telling you something about how strongly you've polarized the medium. Now, the beauty part is that I went beyond the book in explaining to you that there are three different kinds of polarization. There's the ordinary induced polarization. Remember, I talked about induced, which is what I just described. Then we had those which have permanent dipoles. And our classic example was water, Mickey Mouse, plus, oxygen is minus and plus. These are permanent dipoles built into the structure of water. And we said that those have a lot of, when you put them in the field, they reorient and you get a big polarization. And then we had the third case, which was ferroelectric, where these dipoles line themselves up even in the absence of a field. So here I have a table that I wanted to show you. This paper is wonderful. Showing you the dielectric constant. That is the polarization that occurs when you put these in. And you'll see that ordinary materials, paper, polystyrene, oil, Pyrex of glass, mica, porcelain, they're all the ordinary induced polarization stuff. So you get some effect. But look at water, 80, 10 times more. Now you can understand why. Water has permanent dipoles. And when you put it in a capacitor plate, those big dipoles line up and you get a nice big polarization. You suck more charge in. And then, even bigger than that, look what happens if you, where am I? Here I am. Look what happens if I put in titanium ceramic or strontium titanate. Remember I mentioned barium titanate, the ferroelectrics. 300 compared to 3. 100 times more, because you're dealing now with a ferroelectric. So, you see, this table doesn't appear in Wolfson's book because he never explained that there is such a thing as a ferroelectric, so he doesn't mention it because somebody would say, hey, your table, where's this 300 come from? But this is from another book. He has a table, but he leaves out the really biggies like ferroelectrics and these giant ones. So the story is that the point is that with the dielectric inside, the capacitance is multiplied by this constant K, which is called the dielectric constant. And if you ever have a problem where you put some material there, if you want to find the effect of having the material there, you just take the epsilon naught and multiply it by the dielectric constant K. They just go together. Now, the interesting thing is now we can see a very nice relationship between the resistor and the capacitor. Because the resistor, if you recall, was given by the resistivity times the length over the area. So I pointed out to you that you have here a materials factor, the resistivity, which is an intrinsic property. It's the friction that the charges feel as they run through. And a geometrical factor, the length over the area. Now, the capacitor has the same feature. Now that we realize you put a material inside, it has a materials factor, the polarization of the stuff you put inside, and area over L, and a geometrical factor. So it has a geometrical factor and a materials factor. So that's characteristic of these circuit elements. It depends on their shape, area, length, things like that. Also, what kind of material you put in, as you sort of might expect. And in fact, we're going to have yet another type of material in a week or so, which also has this pattern. So it's good to see these unifying features. The other thing that I have neglected to mention in detail is the idea that inside a capacitor, you have stored energy. We demonstrated that when I had this very big capacitor and I charged it up to 1,000 volts and we shorted it and all that shock bang happened. Well, in fact, what happened was I turned the power supply off at one point and the voltage stayed, which said that I put charge on there, the energy stored there, and I only released it by jumping the two. I put charge here up with 1,000 volts between these, and then there's 1,000. I brought a ball in here, and I allowed the electric field between these two to short out, and that produced the bang, because that was like a lightning bolt right in here, like that. So lightning bolt and thunder. It was thunder, really, what you heard. So there is energy stored here, and I won't have time to really derive it. I just want you to realize that there is energy stored there. It's stored in the field. Even if I turn that, I charged it up, but then I disconnected that, and the energy was left in here. And that's a little bit like what John was saying. You store energy in the thing, and you can use it. They also use that when you want to build up voltage and get a high voltage all at once, stored, and then you can discharge it. Like, in these defibrillators or these things where a guy, in these crime movies where they go put two pads on here and they go 1, 2, 3, ka-chunk, they store the energy on a capacitor and they discharge it through the person to try to get the heart to go, the defibrillator. The same process is going on. So please learn about this. It's pretty easy. The interesting thing, though, is that, again, you will have an energy energy. It's actually power, I squared R, in a resistor. In a capacitor, you will have energy stored, it's 1/2 CV squared. So you're going to see some parallels here. You have your circuit element C and the voltage on it. In the case of the resistor, you're going to have, again, something squared. The current and voltage are variables, and this is the material quantity R and C. So, but the difference is here, the energy is dissipated. That is, you put the energy in and it's used up in a resistor. Energy is, we call it dissipated. Or it's used up. In other words, you put electricity through a light bulb, and its voltage or its current is turned into light. In here, you're not using up the energy, you're storing it. So the energy is stored. That's a big difference. So in a good capacitor, you don't use up energy. You put the charge in there, and it just stores up as energy in the field. Now, John's woofer's pretty good, but this is the mother of all woofers. Over at the Livermore lab, the Lawrence Livermore National Lab in Livermore, they have an experiment there. It's $1 billion experiment where they're trying to make nuclear fusion. What they're trying to do is to have lasers come in and hit a pellet of hydrogen about as big as the tip of your finger. They have, I think, 196 of the world's largest lasers, which they fire by firing flash lamps. Banks of flash lamps around these lasers. They have to fire them simultaneously what they do is they start out with one little light pulse. They break it up into 196 copies. They send them into these light amplifiers, lasers. They fire these lamps to try to boost the little pulse up to gigantic amount. Then they focus all those beams on this little pellet in order to the light pressure and heat crush together to try to make the hydrogen nuclei stick together to form helium, and energy will come out. That's called nuclear fusion, and they dream that this will be the energy of the future because it has no radioactive output, and it uses hydrogen, which is water, from water, and there's plenty of it around. So that's the dream, nuclear fusion. So here's the story on this. They have, well, why don't you read it? It's in the notes. They have 12,500 square feet of capacitor banks, which they store up 400 megajoules of electrical energy in each shot. Takes them 60 seconds to charge up the capacitor. Like we did it here, they're charging up that bank. Oh my gosh. Oh, I see, I forgot to use my thing. And they release all that energy in 400 microseconds. So they get 100 million amperes flowing out of the capacitors. The peak power is 1 terawatt, 1 trillion watts, which is greater than all the power being used in the whole United States during that 400 microseconds. They have more power, energy per time, than the rest of the country. So you can see what they do. By the way, if you want to go visit that, you can ask to go, but it's a secure facility, so you would get checked by an armed soldier as you go in. But if you're a citizen and you're not on their bad list, you could go and visit this place. It's very interesting. It's huge. It's like a giant thing. And they're very nice. They take you a tour and you can see it. It hasn't worked yet, frankly, but they're getting closer and closer. It's very delicate. So here's a comparison between the two elements we know, resistors and capacitors. You know, when you put them in series, one increases, the other decreases. If you put them in parallel, the resistors decrease in total, the capacitors increase. In the resistor, the energy is dissipated, and the capacitor, and they both have this. So there are similarities and differences. Now I want to go on to magnetism. I'm sorry at the quick switch, but we need to. Okay, well, the story here is that, of course, you're familiar with permanent magnets. Unlike electric things, we have magnetism. It sort of exists without anybody doing anything. You didn't have to do any friction or anything. People found years ago, in fact, here's a compass needle. This was discovered, I think it was already recorded in Chinese literature way long ago, that some materials line up with respect to the Earth. And they attract and repel each other. You take another one, this is slightly different, but you see you get this action at a distance here, two of these types of materials, and a very familiar idea. And then, of course, we had electricity, which we talked about up till now. But until about 1820, it was thought that electricity and magnetism were different phenomena. But the story was, of course, that in 1800, roughly, we already said, that Volta taught people how to make current sources, constant current sources, big batteries, like there's one down by the foot of the table here. There's a big battery there, and Volta said, I can give you a current through a wire. So the great experiment that was done was by a man by the name of Ørsted. I'm not sure, but he was Danish or Swedish, Scandinavian fellow. And he was a teacher, and he had learned about the Volta's batteries, and he had some batteries. And he set up an experiment like this, where he had a battery, and he was demonstrating this, and as luck would have it, he had a magnet nearby. And I think it was accidental, actually. So he put on his battery, and the magnet turned. Now that simple thing changed the world. That is one of the great discoveries of the human race. So what it means is that now ordinarily electric charge, static, if I had rubbed a fur on a ball and brought it near the magnet, it would do nothing. But if you have current flowing, this was the great discovery. See, because people had known that there was electric, there was magnetic, but nobody's realized there was a connection. But once you had a means of creating a current, then Ørsted could discover that currents by which we now know means charge moving over time, moving charges. They connect with magnets. That caused a revolution. This was 1820. Volta, of course, was already talking about the year 1800. So this tells you that electric currents, in a sense, are magnets. Now, as soon as that was discovered, it electrified, it galvanized, all those good things. The folks around Europe, when Ørsted's little paper came out, and quickly, 1820, almost immediately, the French scientists jumped on that. The French were very quick on these subjects, and quickly measured how much current produces what kind of field, which we call B. Now, it turns out that the current and the field are a concept that we have already encountered with electric stuff. Here, before we had Q, and it would produce an influence E, right? It turns out that this is a source, you see, and this is the field it produces. We're going to follow that analogy right through. Q as a source produces a field, and then what we do is we get a force by putting another object in the field. So you get a force by putting some other magnetic charge in this magnetic field. Just as you got a force when you put an electric charge, Q2, in the field produced by E1. So this would give you the force of 1 on 2. So if you had Q1, it produces its field, and then you put a charge in it. So we build up a theory which follows that pattern, except it turns out that magnets are a lot more complicated. So whereas this field, this force, was sort of radially outward from the charge, so the force was along the line, as luck would have it, with magnets, everything is sort of at right angles to everything else. It's a real... It's conceptually not any harder, it's just that geometrically it's a mess. So I'm sorry about that, but that's what nature provided us with. So in this picture, what you see is that whereas the electric field was in the direction of a radial vector, radial vector, that E was in the direction of the radius outward. With the magnetic field, the current can be in one direction, the radial vector is another direction, and the magnetic field is in a third direction. This sign here is called a cross product, which you may or may not have encountered up till now. But the beauty part is that, in addition, we had, in a case of electricity, a Gauss law where there was an integral over a surface and it had the charge inside, and you could solve some particular problems with the Gauss law. We have a similar law with magnets. It's called the Ampere law, another Frenchman, where you can, if you know the magnetic field, over a line, you can find the current inside that line. But then you have the same form where you have a force is equal to something you put in the field times the field. Here we're going to have, you put something in the field times the field will give you the force in the magnetic force. But again, there is this cross product, which is complicated. So let me show you, remind you what a cross product is. As I say, everything is sort of at right angles here. Are you familiar with cross product? Have you come across it? Have you come across the cross product? Yes? Okay. And in that formula, there are two cross products, which means there's a double cross. And well, anyhow, that's not too funny. But you feel double crossed when you have to do this. The point is that what we're trying to get is a kind of mathematical system whereby we get at right angles of things, so that if you have a vector in the A direction and a vector in the B direction, what is the cross product? Oh, you're starting already. You remember this? Well, my way of doing it, a lot of people have different rules, and you see, well, the contortions. But my way, and I illustrate on this slide, you put your fingers in the direction of A. So I'm trying to find C as the cross product of A and B. So I put my fingers in the direction of A. I turn them in the direction of B. I'm thinking of B is coming out of the blackboard, and my thumb will point in the direction of C. That's the way I do it. Now, some people have other things. They have FBI or some various complications. That you heard of that one? Yeah. I can never remember which is the FBI. Okay, but whatever works for you, do. But that's the one I do. So in other words, if you put your finger here, that's why this thing says turn your A into B. And now the order matters, because this is not equal to B times A. As you can see, because if I do B times A, I'm going to get minus C. B cross A is equal to minus C. So the order matters, which one you turn. Okay. Well, I should put that there. So in fact, in my notes, look, in the book, they're going to say, you use the right-hand rule to do this, and then you use the right-hand rule to do that. Turns out there were 3 different right-hand rules. So you have to know which right-hand rule they're talking about. So I've collected them here. You use one right-hand rule to find the direction of the current of the field around a wire. You need another right-hand rule to find which way currents go around through an Amperian loop. And there's a third right-hand rule to which way the force is if you have a current and a field. So there are 3 right-hand rules. You follow my notes, you'll sort of be led through it. For example, we have an example of a wire, which you can solve using the BO. Well, I didn't even say what it is yet. But we have a rule here where from the current you can find the field, and it's very similar. There's a source, which is the current times its length, cross R. So there's your source over R squared. So it's very much like Q epsilon, 4 pi epsilon naught over R squared. The field of a point charge. This is the field of a current element. You have a current that has a certain length, but you have a mu zero up here. So you see that it turns out that the field falls off as R squared from a little element, just as with electric field. So if you just remember your electric stuff, you can dope out the field. And the second one, way of getting the field is by this general rule of Ampere, where you get the magnetic field around a loop, a so-called Amperian loop. And with that, you can, if you have current and go in this direction, you go around a loop, and you will find the magnetic field. It goes in loops. Now, I don't know that I showed that. not too obvious. But I tried to show that, you see, the magnetic field is actually going, see how the magnet is lining up? Hopefully. Yeah, you see it changes direction. It's trying to line up the lines of magnetic field. Oh, the current is going this way. The lines of the magnetic field are circles around here. And this dipole is trying to line up with the lines, just like a dipole wants to line up with a field. So it's trying to line up with that field. So the field lines are circles around the wire. That's another tricky thing. Again, the current is this way, but the field is that way. It's not like the electric charge, where the charge over here, the field would be that way. No, in the magnetic thing, the field is that way. So you got to get used to that idea. And the other thing that I quickly will show you is that once you have a current flowing, now here's a very nice demo. It's even better. Yeah, I've turned on a kind of a neon light here. Now, what it is, it's a beam of electrons going across to neon light. Now, these are charged particles, so this represents a current. If I bring a magnetic field near here, what's going to happen? You see there are a couple of electrodes above and below. If I can bend the beam, it'll touch one of the electrodes, and maybe, see over here, there is actually zero. We've offset the zero so that we can see it go both ways. But if I put a magnetic field here, what's happened, again, there's one of these right-angled things. I'm putting the field this way, the current is that way, and doggone it, the thing moves that way. It moves in the third direction. So I can actually bend the beam, I think, and you see, I'm pushing it in one direction, upward. So the beam is going upward when I do that, and I can move it the other direction by reversing the direction of the polarity, go the other way. Now I'm bending the beam in the other direction. So it's one of these sad things that we have to deal with right angles. Now, I regret that there's so little time, excuse me for that, but today is a special day, actually. View. Today is close to the birthday of Galileo. He was born on February 15th, 1564. He's getting older. But he's one of my favorite great heroes because I don't know if you know the story of Galileo, but he was a genius man and very courageous. And he was the one that challenged the current wisdom of the time. And, of course, he was punished badly for it because the Catholic Church didn't like some of the things that he had discovered, namely that, and I played the music Jupiter, he built his own telescope, and he looked up at the sky, and he saw that there were moons going around Jupiter. Now, the thinking at that time was very poetical, namely that the earth was sullen and evil, and the heavens were perfect. What does it mean that the heavens are perfect? That means that everything goes in circles because the circle is perfect, and that the heavens are unblemished. Galileo looked up with his telescope at the sun and saw there were spots on the sun. Spots on the sun. So I thought it was perfect. It's blemished. He looked at the moon, and there were craters on the moon, and he drew pictures of the craters. So the heavenly bodies were not perfect spheres and smooth and, gorgeous. And moreover, the thinking of the time was that everything revolved around the earth. The sun, the moon, everything. The earth was the center. And nothing could revolve around anything else, but here were moons going around Jupiter. So, and he said, in fact, that the earth was moving around the sun. that seemed to discourage people. He also had noticed, that by sitting in church, I guess he was bored, he noticed that the pendulum, the chandeliers were swinging at a certain rate. Regardless of how big the amplitude was, they always went at the same rate. He said, oh, wow, that gives me a clock. So he invented the pendulum clock, which they didn't have a good clock up till then. He also understood that a thing moving, you would never know that it's moving. He used the analogy, if I'm a sailor in the top of a ship and I drop a sack from the mast, it'll fall at the bottom of the mast. It won't fall off the back of the ship if the ship is moving. Because the sack is participating in the motion of the ship, and if you just keep it going and you let it go, it'll fall straight down because it's going actually sideways too. That's why he understood that if you're going in an airplane 500 miles an hour and the stewardess pours you coffee, the coffee doesn't go flying away. It doesn't. Why? Because the coffee is participating in the 500 miles an hour. So it falls, in your frame of reference, it falls straight down because it's going with you. Unless the plane jerks. Then, of course, it'll end up in your lap. But, I mean, so he understood all those things, and he got him in a lot of trouble. And eventually they put him on trial. And rather than burn, he said, I'm wrong. I abjure. I give up my beliefs. He said, I abjure with sincere heart. I curse my errors. Sorry, I put the paper back. Okay, yeah. So this is fabulous. That they made him, I abjure, I curse the lies that I said. So they put him in a house arrest, and they wouldn't let him talk about the stars anymore. But it all is not done because 350 years later, the church said, well, maybe they made a mistake. The other thing that I love about him is that he appreciated creativity. He said, nobody understood that the earth was a magnet. We take it for granted, but somebody had to see that. And here he wrote a thing honoring the man who first said, the earth must be a magnet because it's attracting other magnets. And he says here, to apply oneself to great invention, starting from the smallest beginnings, and to judge the wonderful art that lies hidden behind trivial and childish things, to see those things is not for ordinary minds, but for superhuman souls. In other words, you don't have to do these fancy little things. Just open your mind to the simple childish things. If you can explain the little things, you probably have grasped something great. So the fact that Gilbert could recognize that this was a great discovery. Okay, so in honor of Galileo's birthday, we have a party. Italian cookies. Very, very nice. Bene. Come on out, grab some cookies, and on your way out, have something to eat, and thank Galileo. He's a great man.